And then that is okay. No, it's okay. Thank you for doing that. And welcome to those joining the recording. And then a few years later, computing sits at the crossroads of applied mathematics, science, and engineering. The three processes are of equal importance in the discipline, which is a unique blend of interaction among theory, abstraction, and design. So I felt like this was a really important definition to show here when we're all bringing in our different discipline-based knowledge. We're coming from math and science and engineering. And so I'm not different than y'all. I'm a combination of everyone. No, and so it's all a collaboration. Computer science is a collaboration. Computer science education is no different. It's all a collaboration among different things. And also, this is not just talking about algorithms, but also how there's different steps that you can think about computer science. So it could be theoretical, you could be designing things or abstracting things. I also wanted to take a moment to show you things. So a lot of times computer science just gets boiled down to programming or coding. Yeah, it's easy to just do that, which I'm going to do. I feel like I should pay some homage to that. And so when you hear me say coding or programming, I wanted to like display a couple of things that might mean. So we're going to play around a little bit. So this is Scratch. Scratch is a programming language developed out of MIT. And it is primarily used with young students learning computer science because it allows a lot of creativity depending on how you approach it and teach it. So there's a lot of interaction. This is called the stage. So there are actors or sprites that go on the stage, and you can program them using blocks, which we'll see in a minute. So this program just has the fish saying, hello, welcome to Scratch. Click the space bar to see Helen the Amazing Crab change colors. And if I do that, then she changes colors. Woo! Yeah. You're like, that's not programming, Miranda. Okay, I see you, I raise you. So these are blocks. And so this is a block-based programming language. You can click it, you can drag it around, you can change the different numbers. And so this is controlling everything that Fred the fish is doing. You can also see what Helen is doing. Why is she changing colors for so long? Oh, well, it's repeating for 30 times at a second a time. So it's going to go on for a little bit. But now she's stopped because it's been 30 seconds. Also, when this sprite is clicked, she'll say, ouch. So let's just bug her. Ouch. Okay. So this is Scratch. This is a programming language. There are also two AP, Advanced Placement Computer Science courses, APCS Principles and APCSA. So these both link to ebooks, which I was involved in a lab at Georgia Tech that built ebooks for these courses. So they're all browser-based and free and have ads, so you can see that I've been shopping furniture for my office. And yeah, now that they're all loaded, interactive too. So it has fill in the blank questions, but it also has coding that you can compile in the browser and you can see the output. So here it's just saying, well, 4 plus -2 times 3 is equal to a result. Let's print result, which is -2. That is faster than I could have done it. But you can also change it. It doesn't have to be exactly what's here. And so a classic computer science thing is to print hello world in each language. And so we save and run it. And so now it prints result and hello world. So that's showing off computer science principles. We also have computer science A. So principles is the first course, a fundamentals course for AP. APCSA is the next course in the sequence. It's a little bit more advanced. It goes into more depth, more programming. And so this one is nice because you can start to see like those blocks that we were dragging around earlier, what that looks like equivalently in text code if you were to write it out. And then also I wanted to show off that the programs start to get more complicated. but you can still run it in the browser. And in this case, it actually has tests that you automatically fail because you didn't do anything to it. And so I just wanted to take the time to be like, this is a little bit of computer science. This is a sliver of computer science if I'm reducing it to just programming. But now you can say you've at least seen code if you haven't before. And it's not just like the matrix code, right? Sliding on the screen. So that's a little bit about what computer science is. So bringing it back to CS for All. So CS for All, equity movement to allow all students and teachers to learn computer science. Because one of the biggest differences between me and you is your fields are in every school typically, right? So math, every student has to take math to graduate, many math courses, science, everybody has to take science to graduate. Computer science is not required by most, I think now they finally said, I think 27 out of 50 states. It just came out, have some sort of requirement for computer science for high school. Last year's report revealed only 51% of high schools across the whole country teach any foundational computer science course. Half. So that's how many schools are just offering the course. So that then begs the question, how many students are taking it if only half have it? And let's do that. 4.7. It's a small piece of the pie going on here. 4.7% of all high school students participated in a foundational computer science course last year, 2021. And you might be like, oh, well, we live in California, we've got Silicon Valley, we've got a lot going on. That's a great question. I'm glad you asked it. You do have a lot going on. It did improve. And this data is from CS for CA, Computer Science for California, which is a coalition. So CS for All can mean a lot of things to different people, depending on if you're talking to NSF or who. But there is a consortium called CS for All, and then there are state coalitions that also use those as their names. So CS for CA for California, CS for GA for Georgia, and you don't have to follow that metric, but just so that you know. And so in San Diego County, it's only 4% of high school students. So it's less than the average for less than the average for both nationwide and the state of California. And you might say, okay, well, that's not a lot of students. Who are these students though, right? Like many STEM fields, computer science is not different. We have a number of representation problems. So we are overly male and overly white. It is not different if you look at the high school students that are taking these courses. So it's about 70%, 70-30 male to female ratio for high school computer science courses across the country. And then race and ethnicity, 50% white. And those numbers are changing every year, but it's not a great representation of the country. And then looking specifically at California, which we'll look at it here and then we'll play with a dashboard for a minute. So right, we already saw that there's 5% of students in California enrolled in CS courses. It's the same divide as nationwide, 70-30 boys to girls, and similar split across racial and ethnicity categories. So as I mentioned, CS for CA is the coalition across the state that's, there's people in higher education, so Beth is a part of it, but there's also people in nonprofits and community colleges and K through 12 schools, and policy workers that are working to change the field of computer science. And so they've put together this data. It is from 2018 to 2019. They update it when they can, but there's usually a lot of education data. And so this is pre-pandemic, and it will be interesting to see how things changed as a result of that. But so this is the statewide look at things, and you can always They have nice little tooltips so you can see which county is out in the lead, and you can compare things, but you can also narrow it down. So I can't spell San Diego, that's a good sign. So you can narrow it down to see what your county looks like. So it's below average, like we saw with the pie chart, compared to the rest of the state. And you can tell the gender and race and ethnicity enrollment. And then you can narrow it down in even further. So let's go to San Diego Unified. And that changes a little bit. It is actually, San Diego Unified is actually above average at 5% enrollment across the county for high school computer science. And then you can narrow it down even further to the exact school and type of CS, which is fun to play with and get to understand the landscape, but also a little sad. It's fun when the numbers go up, but they're not going up by a lot year to year. So that is our discussion of what the landscape currently is regarding access, and what computer science is, what computer science for all is. I do want to briefly cover my research. And so I have a huge slide here saying computer science education research. I am not representative of the field and subset of it. Just have to put that disclaimer out there. But so I'm going to cover a lot of the different work that I've done, and it's going to be super abbreviated. So if you have questions, I will happily talk more about them because each of these things are a talk in and of themselves. So we're going to see how coherent this is. But I want to start by framing my work. So access, assessment, and achievement, right? And those start to show up here. But I basically have two steps in my work. I work on understanding the factors that inhibit equitable computing, access, and achievement. So not just are they stepping into the classroom, but once they step into the classroom, how do they perform? And then using that knowledge and understanding to create low-cost interventions to mitigate those factors. And so, yeah, we'll step through each of these. So first up, access, because we just finished talking a lot about access and what students are able to access across the state. So this is my, let's see if I can get rid of this little bar. No, it's not. We're just gonna slide it down. Yeah, you don't even know who I am. So my dissertation work, well, yeah, we're clear now. My dissertation work was based in the state of Georgia because I was at Georgia Tech. And so I looked at different factors that affect computer science enrollment and offerings across the state in high schools. So I looked at 3 different variables to start. Median income of the county, school enrollment. So I was looking at all high schools across the state, all public high schools, and whether the school was located in a suburban area or not. So that was just a binary factor. And I loaded those into a model to see if it predicted if a school had any computer science, just is there computer science or not. It did reasonably well. Median income and school enrollment were significant factors in that model, not whether the school was suburban or not, which kind of goes against some of the prior literature, which is a little bit interesting. If I added in if the school had computer science the year prior, that significantly improved the model. It explained a lot more variance. And so what this is, oh, and there is another slide here. If a school had computer science in 2015, it had an over 2,000% increase in the odds of offering computer science the next year. So if you have computer science, you're likely to continue to have computer science, which makes logical sense. But as I said, CS education is a relatively new field. That was not kind of knew it, but we didn't know it. So hey, we showed that. So then I moved on, instead of just if they had computer science to how much computer science did they have. So I had the same 3 variables of median income, school enrollment, and suburban status. I also added in percentage of students from traditionally overrepresented groups in computer science, percentage of white and Asian students, and the average prior CS enrollment based on the previous model. Average prior CS enrollment was the significant factor in that model, to cut it short. There is predicted increase of almost 2% of computer science for every additional percent increase from the average prior year. So not only, just to put it in simple terms, not only if you have computer science, will you continue to have computer science, you will continue to have it and grow it year over year, which then begs the question of, okay, well, how do you start offering computer science? If this is such a pivotal part, like, okay, you have computer science, you're just going to offer it and have the momentum then. How do you start offering it? So then the other half of my dissertation work was actually visiting schools and talking to them, talking to people. So I visited 4 high schools across the state of Georgia, selected through cluster analysis, and they all had different situations going on. So none of them actively had a computer science course. 2 of them had computer science previously, but didn't anymore. So that went against my model. How dare you? But it provided an interesting case study of like, okay, well, you had momentum. How did you lose it? One had never had computer science, was not interested in having computer science. And then the last one had just finished registration for the following year and had gotten it on the schedule. And it was such an exciting time for them. And so I got to ask them like, how did you get to this point? And it was very fresh in their minds. So after interviewing them and thematically coding those interviews, I came up with this model of structures and agents that influence schools offering a computer science course. So it's not just one piece. It's not like you can just increase the number of computing teachers and expect computer science offerings to go up. There are other factors at play, and they all work within each other. So that's why it's gears within a system. And if one gear is missing, then it may not work at all. So for the 2 schools, Cobalt and Marigold previously had computer science and didn't anymore. It's because the teacher left. And because the teacher left, then the course left. And then they couldn't operate. They still had students interested. The community was super interested. They still wanted it badly. And the principals mentioned that multiple times, but it wasn't enough to offer a computer science course. At the school that didn't have computer science and was not interested in offering computer science, well, they didn't have a computer science teacher, but they also felt like they didn't have the resources. So they felt like they didn't have the equipment appropriate to offer a computer science course. Which was an interesting discussion of perceptions of what equipment do you think you need for a computer science course. Policies, they had the lowest graduation rate of all the schools that I visited, and so they were very keen on improving graduation rates. They felt like offering a computer science course would not help them as much in that goal, as much as offering more algebra courses and supporting students in other ways. But they did have community backing. They were like, oh, if we offered it, students would totally take that. But we just aren't interested right now. And then the school, not surprisingly, that had computer science on the schedule for the following year, all of these pieces came into play. And it was really interesting to talk to the principal and the registrar and the teacher to really unpack that. Each of these years got added slowly over time. They made a very intentional effort to offer computer science, and it was over a series of time. So the school administration came together and said, yeah, we do want to build this interest. They built interest with their students by starting with cybersecurity first, also doing cybersecurity clubs and other options, and then making announcements. And then the students were like, yeah, I want to take cyber. And so they had a teacher that had a cybersecurity background and was teaching English. And he was like, I would much rather teach cybersecurity than English, actually. And so he was able to transition. Asking him to transition from cybersecurity to computer science, not as easy as you might think. He was a bit intimidated by it until he went to a professional development. And he said almost word for word, yeah, I can do this if that's all it is. So yeah, but it worked for them. And so all of these pieces came together to allow them to offer a computer science course, which is awesome to see. So that's about the understanding the factors that might inhibit equitable computing access. Now talking about achievement, which if we're keeping track of the A's, I'm also tying in like assessments with achievement here. So I've worked on a couple different assessments in my time. So the first one that I worked on is called SCS1. It's the second CS1 knowledge assessment, which is a little bit of a confusing name, but it's not original. It was replicated from the foundational CS1 assessment, and we were like, how do we keep it similar enough so people know that it's second, because it's the second one, cool. But then people are like, oh, is it for the second course? No. If I could go back, I would maybe change that. And so this was meant for introductory computer science courses at a college level. Computer science is fun for a variety of reasons, not least of which because we have multiple programming languages. You saw a couple earlier. At Georgia Tech, where this work is done, the intro computer science course is taught in MATLAB if you're an engineering major, Java if you're a computer science major, and Python if you're not either of those. So the person who created FCS1 said, well, I want to compare outcomes across these courses, but how do I do that across 3 different programming languages? Well, I make an assessment that's valid across all 3. So it's written in a pseudocode. So it's a multilingual assessment, which I recognize multilingual means different things to different people. And we haven't come up with a better term in computer science yet, but multilingual programming languages. And it covered 3 different asked questions in 3 different ways. So kind of moving along with Bloom's taxonomy, understanding, analyzing, evaluating. So it was not just what is a for loop, but also tracing through segments of code and saying what is the output of this, and code completion, which this is a multiple choice exam, so they're not actively writing code and completing it themselves, but we do have like chunks missing from the code and ask, okay, what chunk should go there? And across 9 content areas that were found to be most common in introductory CS courses to make a 27 question assessment. And this has been a really exciting project. My advisor, when he introduced it, did not undersell it. He was like, yes, I have this project you can work on. It's very well contained. You will definitely get a publication out of it. And I think it will be cited a lot. Are you interested? And I was like, yeah. I mean, why would I say no to that? So it's been used, including by Leland and Sasha here at San Diego State, portions of it. It's been amazing to see how the community has adapted to use this, because we don't have a lot of validated assessments in computer science, especially those that are open to the community. So there's been a lot of different research projects that have taken this on, which has been great to see. I also worked on a totally different kind of assessment. When I was at UC Irvine, that's what I was hired for there. We called it ACES, Assessment of Computing for Elementary Students. So this was for 4th graders. And a totally different audience than undergrad CS majors. And so just like, how do you ask them questions? This was also during the pandemic. So how do you have them answer questions on a survey? How do they finish was a big challenge. But so this was very narrowly scoped to just cover 2 concepts in computing. It was sequences and loops. And then we asked the questions in 2 different ways. So in one way, it's a coding question. You can see the code blocks. It's animated, which keeps it a little bit fun. And then non-coding questions, but still getting at the same sequences and loops concepts. That was a really fun project. It's grown from initially it was a 10-question exam. Now it's a 20-question assessment. We just released it out to the community last week. And the goal for this is to use it in a randomized control trial. So we had to really dot our I's and cross our T's to make it work for our audience. But that was a fun endeavor. So that is a little bit about the assessments and achievement. Sometimes I combine the 2, talking about access and achievement. So one of the projects I did in grad school was looking at socioeconomic status and how it affects computer science achievement. We know that socioeconomic status is correlated with higher CS achievement, but that's not causal. Having more money does not automatically make you better at computer science. But what are the intermediate variables that might be at play here. So we looked at just two. We looked at access to computing. So that might be summer camps or having access to computer science in high school or elementary school, which is correlated with socioeconomic status, or spatial reasoning, which let's see if I added the slide in the right place. Yes. Okay. I've finally caved and just decided to include a picture of what I mean by spatial reasoning. So spatial reasoning is the ability to, if you're a spatial reasoning specialist, I'm probably going to get this definition wrong. But in this example, it's the ability to rotate shapes and understand what that shape looks like in a different space. There are different dimensions to think about spatial reasoning and spatial skills, but that is the specific one that we looked at with this study. And so that might be socioeconomic status gets you more access to spatial toys. So Legos, for example, as a kid, which increase your spatial skills, which increases your computer science achievement. So we looked at these. It turned out that access to computing was not significant in our sample at all. It fell out of our model. Spatial ability, however, was a significant mediating factor at play here. So that was really fascinating to see. And just to go back to that, right, the second part of my research is leveraging low-cost interventions. Spatial ability or spatial skills is not expensive to train. You can teach spatial skills and over a short amount of time and have huge impacts on CS achievement. So this work has been used by people to motivate the work that they're doing in spatial skills training. And that's work that I hope to continue here as well. Also talking about low cost interventions, we saw the ebooks a little bit earlier. That was a lot of fun to work on and do some participatory design with students to understand, do they know what they want in a ebook? Answer is no, but it's okay. And specifically, I looked at how teachers and students were learning the ebook or using the ebook, because our teachers were learning computer science for the first time, right? Maybe a week ahead of their students. So we were like, oh, what's the differences here? The difference is that teachers are expert learners. They know how to learn. They know what is good for them. The students, not so much in this case. We had a fun finding of the students would run code in one of those boxes and it would flash red and say, you have an error. And then the next thing that the students would do is run the code. They didn't change anything. They just ran it again. And then they would just like continue. And it's like, oh, that's a really interesting. I wonder what is it magic? I don't know. Did you think something would switch just by pushing it enough? Teachers did not get stuck in that loop. So that was a little bit interesting there. And I also worked as part of an international working group, my tiny name in the corner, to look at the literature that's out there for broadening participation for women in computing. I mentioned earlier, there is a gender gap in computer science. There is a lot of work that's been published that focus on women in computer science programs. And they say, yeah, we improved the ratio. We wanted to understand exactly what out of that is working and do a big group with a big group of people, or a big project with a big group of people. To save you from reading 80 pages, and hopefully these are not surprising findings for you, removing stereotypes, really good practice to increase representation in computer science. Using collaborative learning, active learning, peer instruction, think, pair, share can help increase the ratio there. Making connections to student interests. So I had this slide in my job talk when I was here back in February, and back then my example was a bit more relevant, but it was, you may be interested in Wordle, but your students may not be. So if you have to program Wordle, you know, it may not be motivating for them. So connect to their interests, not necessarily yours, and having positive, meaningful interactions with students. Right, it should not be surprising, and yet these are things that we can do to improve representation. So future work, which, you know, future now, I guess. So there's a lot of existing projects and ecosystems in computer science in San Diego. Computer Science Teachers Association is a nationwide organization, but they also have local chapters. They have a very active chapter in San Diego, which is fantastic. There is Computer Science for CA, which I mentioned earlier. Beth, I sampled out her projects here, but there are other projects going on in San Diego too, but actively funded by National Science Foundation and working with Computer Science Teachers Association to work towards broadening participation in computer science in San Diego, which is a fantastic ecosystem to be a part of. And other peers at UC San Diego that are doing great work as well in other directions. What am I interested in doing? I'm going to continue working on assessments, the two that I mentioned earlier. I joke that I will always have a job because there's always more to do with assessments, for better or for worse. And so there's some active work going on with those. Continuing working on improving representation of women undergraduates in computer science. I'm still working with some of the members from that working group earlier and hoping to propose a new working group in that thread. I say new thread, but going back to the spatial skills work that I did in graduate school and really honing in on that, I think that's an opportunity for a huge impact here, and not just in computer science. Do it in math and science as well, and really understanding what can we do for our students to support them, and also looking into the pathways from community colleges. I am currently teaching a software systems course. I have 48 students, about 90% of them are in their first semester from a community college. And I'm doing the best that I can to support them, the best that I know how, but what more can we do to support them to allow that to be a viable pipeline for our students? And because I am in a bubble, I do welcome being outside of that bubble. So if you have ideas, or I also welcome collaborations, I look forward to discussing all of that. And so with that, to thank you for getting through the talk with me, I included a picture of my dog, Cassie, and she's excited. I'm excited. We're all happy to be here. And with that, thank you. I'm excited to take questions.
And Miranda, do you want me to moderate questions, or do you want to take care of there and Michael? I am monitoring the chat. I think.
Oh, if you have it up, then go for it. Yeah.
There's none in the chat yet, but if from the room.
I see Jenna. Yeah.
That was awesome. Thank you so much. I learned so much about a field I really now realize I didn't know a lot about. You alluded several times to reasoning, student reasoning. About computer science, and it was often observations that you had made. Yeah. And I'm curious. I mean, and I find just reasoning about all sorts of things fascinating and drawing out everything from students. And I'm curious if this is something you will formalize into research projects. I mean, some of the coding languages that did you develop the fourth graders that?
I developed the assessment for it, but not the language. Yeah.
I mean, just such opportunities to understand, reasoning about sequencing and such. And I'm just curious if that's a research area of interest of yours.
Yeah. So actually, that's a great question. So my very first, you only have so many slides. My very first CSN research project was in a course at Harvey Mudd, and it was understanding how students understand Big O, which is a concept in computer science. It's not important what it is, but students were having a hard time learning it, and I was like, why? Like I had a hard time learning it. I want to understand. Oh yeah. Or stop share. Stop share. Yeah.
Yeah. Stop share.
Yeah. Oh, cool. Awesome.
Show maybe your review.
Oh, I see.
In video. Is that what you need to do?
No. This
Show.
Go out of screen view. Don't.
Yeah.
Rather than have group.
Yeah.
View.
This is okay.
Oh, yeah, okay. Right. So understanding how students understood this concept, and it was fascinating to get an inside look of their cognition through like think aloud interviews. I thoroughly enjoy doing that. And it was actually funny, at some point in my PhD, my advisor was like, "You're a quantitative researcher." And I was like, "Since when?" And he was like, "Since all of the papers that you publish are quantitative. And I was like, oh, but my first project was qualitative. I enjoyed doing that. And it's something that I've been trying to get back to, and especially with the assessments lend themselves well to doing those types of work and breaking them down. And especially like the world is my oyster when I add in like spatial reasoning skills and understanding. And there's been some work of students, especially like tracing and sketching their process as they go through code and how they understand it. And if you tie that into like, well, how do they even reason about 2D and 3D spaces? Does that affect it? I'm very interested in that, in short. Yeah.
That's really, I mean, that intersects so nicely with your questions about how we best support college students or high school students in the learning of these topics.
Yeah.
Very cool.
Thank you. Randy.
You shared a really engaging story about your own personal journey. I'm thinking about the fact that we need more people to learn about computer science, K-12. And I happen to be the interim director of the School of Future Education. And so I have my thoughts about preparing teachers to do this. And I don't know if there's no question here. It's just, there's a whole bunch of issues here. And I don't know how you're thinking about any of these, or how big is the job of creating a cadre of teachers, getting them hired, making differences in the schools.
Huge. Yeah. Yeah, it's challenging for a number of reasons. And I am interested in taking it on, but not by myself. And it's definitely something that needs to be a collaborative, and there's no single person that can solve this. But right, what are the outstanding issues? The people who are currently teachers most of them have not ever taken a computer science course. Beyond that, they don't even know what computer science is. That came up in my interviews with high schools as well. The computer science teachers were like, I don't get students recommended for my class by other teachers because they don't know what I do. And so I can't even like get people into my classroom that way. There is significant challenges to being certified, whatever certified means, in computer science, being allowed, having permission to teach computer science in a classroom. That varies state by state because the nature of the United States education, but that means that every state has a different policy. California has a supplemental authorization, which means that you don't get certified to teach computer science. You get certified to teach something else, and then you add on computer science later. Convincing someone to add that on, significant challenge. Especially when you don't even know if you're going to end up in a school that can offer computer science, that will have students like that, right? There's so many factors going on. And so it's important to solve. I would like to be optimistic and think that it is solvable in my lifetime, but baby steps for sure. Yeah. Does that address like some, yeah.
You did a beautiful job.
Yeah, I'm really curious about how you're dealing with exactly this issue you're talking about, which is integration. So this is, I'm thinking, for example, San Diego Unified Recited is offering a course called Course Kata, where they're teaching a bunch of math teachers to teach data science. They're teaching these teachers to code in our studio.
Yeah.
It's all kind of baked into their professional development training.
Yeah.
So I'm curious what and how the integration of computer science into other domains,
Yes.
like data science, like discrete math, for example, something Bob and I are really interested in,
Yeah.
and the training and the monitoring of those own teachers' learning and how it goes across time. How are any of those topics being dealt with, and if so, how?
Yes. So at different levels. So I'll speak broadly, and then I'll speak about some of the projects that I've worked on and am actively working on that didn't fit with the narrative. But I'm glad you asked the question. I could have planted you. Yes. There is work being done to try to train people in other fields into computer science. One of the interesting, and you may know this, but in many states, and Beth can correct me if I'm wrong, in California, business is a certification that qualifies you to teach computer science. Because of where computer science is housed in the career and technical education area. And it's sometimes very hard to convince business teachers that you want to teach computer science. And so, right, I think data science is a very interesting area, and I'm excited to see where that goes as everyone tries to figure out where this data science goes, because I think that's a good on-ramp to computer science education work. And so there is work ongoing at the teacher preparation level. A couple of anecdotes. When I was interviewing teachers at schools, and I didn't always interview a computer science teacher. Sometimes I interviewed a business teacher or someone adjacent to it. And everyone talked about, oh yeah, I do integrated activity. I do computer science activities. I just don't teach a computer science class. So a business teacher was using Sphero robots in her class as an enrichment aspect of it. And these are things that we can't quantify or capture systemically. I'm on a project, it recently was codenamed CIA, which I do appreciate, for computing integrated activities. And so we started by looking at what are the different integrated activities. So, right, this isn't so systemic as preparing teachers, but what are the things that teachers can pick up and use in their classrooms in math or science or English or social studies. We looked at the ones that are specifically block-based, so like Scratch that I showed earlier, and analyzing what concepts are they covering, how do you do that? And now we're growing out the project to look at not just block-based, but other programming languages. And the part that I'm really excited about, and I have no idea how they're going to do it, but they're very optimistic about it. I was like, I'm on board this train, is to try to quantify that. They're based in the state of Georgia. And so they have connections with the Georgia Department of Education, where they're able to, I believe, survey a wide number of schools and somehow manage to capture that in a reliable way. Because we just don't know how many students are even getting these informal glimpses of computer science. Yeah. Kristen, you had a question?
Oh, it's kind of already been touched on a little bit, but I feel like in my experience with computer science and with all education discipline fields, nobody's like talking to each other at all.
Yeah.
So like at a math conference, there'll be a mathematical reasoning sector of it that will talk about spatial reasoning and will go in depth about these ideas, but they don't even talk to computer science at all. Have you found that in CSS?
Absolutely. Yeah. And it was really interesting. Speaking of data science, I went to one of our main conferences back in August, and there was a person there who gave a lightning talk, a pitch to the community, and he was actually from Stats Ed, Statistics Education at UPenn, and he was getting into data science. And so it was his first time at this conference, and so I was like, how did you find it? It's a small conference, it's a small community. And so it turned out that he looked at we have a board, a computer science education board as part of our professional society. He looked at who was on the board. He reached out to someone, it happened to be Leo Porter at UCSC, who is the friendliest person to possibly reach out to. And Leo was like, oh yeah, you should go to this conference. It's in Switzerland this year. Why not? And so, yeah, he came to Switzerland to meet us and give a pitch about how. And so it was so fascinating because I know statistical thinking is like a big thing. That's not that different than computational thinking, which I purposefully left out of my presentation because that's a whole bubble that I didn't want to touch. But that's a whole area that, like, why aren't we talking to each other and comparing these things? And why do we all have to have our own flags in the ground? It's not necessary. And I think especially with areas of data science, there are so many disciplines. I mean, even just looking at college level, where it's or institution level, like where it's being housed in the different departments is really interesting and provides a lot of opportunities for overlap and interaction there. So yeah, we definitely have a bubble, and part of that comes from no offense to Leland and Beth, but right, a lot of people in the community come from computer science backgrounds and then go into computer science education. The idea of being trained in computer science education is really new. So yeah, it's a problem.
Because until recently, you couldn't get a job until you were training in computer science.
Yeah, the fact that this job hall had computer science education in the title. Thanks, Leland. Yeah. Yeah.
Oh, it's my mom. I work with.
Yeah.
So love to talk, and I think there's a bunch of kind of smaller questions here.
Yeah.
So when you talk about participation rates, it's like 4.7 or 5%. Is that the percent of students that are taking one of these classes at that time? Or is it the percent who have taken that at some point in their high school?
It is at that time. It is not a cumulative, by the time they graduate, this percentage has taken it. That's a little bit harder to capture, but I believe they're trying. So that number, like the original 4.7% came from the 2021 State of Computer Science report, which is released by code.org, as well as Computer Science for All, which is an organization, and ESEP, which is Expanding Computing Education Pathways Alliance. And so they all come together and they try to combine their data sources and see what conclusions they can draw. And code.org has been pivotal in tracking the different state policies across the country to understand who has what where. So right, we don't have a good glimpse on how many students by the time they graduate high school have seen computer science at all. Ideally, it's bigger than that number.
Yeah, I mean, it might turn out to be like four times larger.
Yeah.
That would be a really interesting question.
Yeah, absolutely.
But yeah, I agree. It's much harder to track. So maybe the situation is quite as bad.
Right. Right. It's just in a given year time lapse. Yeah.
And if nobody else has questions.
I think there's one more.
Got a couple of students.
Okay.
So I was curious, with that high school you mentioned, they were interested, but you mentioned for high school,
Yeah,
there was one that was specifically interested, but they were too concerned with
graduation.
graduation rates.
Yeah.
So what I was curious is, do you know if there's much studies done on like students' performance flatlining or improving or going down or whatever, after taking a computer science class and other academic courses?
I don't know that there is much work actually on that. I think if there is, there's not a lot.
So I was thinking if you can show a positive correlation,
Right.
then you can make a case for even someone who's concerned about that sort of thing, like it will actually help that as well. Like,
Yeah, and when I present that findings to computer science education researchers, they're like, that's bogus. It would totally help graduation rates. But like, how do you communicate that to the stakeholders? How do you communicate that to the principals? Then how do they communicate that to their superintendents and the parents? And then like, I didn't even touch on like the issues of scheduling on high school thing, right? Like, how do you find time? So yeah, it's a very, that's a good future research direction. So,
I'm gonna just jump in real quick.
yeah.
We are at our time officially, but this is designed to be a brown bag or opportunity to go talk. We're not all eating right now because we're wearing masks. However, the conversation should continue afterwards. That's the intent. So I want to formally mark the hour and thank Dr. Parker for her presentation today. With that, I will officially kind of end the Zoom meeting and the thing, but please continue the conversation. We are so delighted to have everyone here and so great to have this conversation. Thank you.
Okay, so I'm still here if there are.